So what I'd like to do today is outline for you the results of two papers that I wrote with Willie Fischler. These are the FTH numbers over there in 2016. And the import of those papers, among other things, is to say that the standard law, which everyone, including us, believed in for a long time, starting with work of Polchinski and Susskind and numberless other people who contribute to this. The standard law was that you could reconstruct the Minkowski space S matrix in flat space by starting with correlation functions in a conformal field theory, which we all believe are the observables of quantum gravity in anti-de Sitter space. And if you had a model where the anti-de Sitter space could be taken to infinity, then in that, or rather a sequence of models, then in that sequence of models you could construct amplitudes that converged to the Minkowski S matrix. Now there had been some criticisms of those arguments due to Steve Giddings. Most people, including myself, had concluded that those criticisms were invalid, particularly after the Mellon transform form of AdS amplitudes came out. And as you'll see, the criticisms that I have to levy against this point of view are not related to those of Giddings and don't have to do with diagrams like this one, where I think about a finite number of point correlator in AdS space which converges to a Fock space matrix element of the S matrix in Minkowski space. Rather, I'm going to give you two sets of arguments. The two sets of arguments at the moment don't really have much to do with each other. The first set, which historically came second, is an entirely old-fashioned S matrix argument. Has nothing to do, I believe, with anything but kinematics and S matrix unitarity and the rules of S matrix theory. The second argument is based on the holographic space-time formalism that Fischler and I have been working on for about 15 years, and gets another aspect of the discrepancy between the flat space and AdS results. So let's start with the flat space argument. And the basic idea is the following. The basic thing that's problematic is that in Minkowski space, you can have gravitons of arbitrarily low energy. So if I think about, for example, some perturbative string theory background, I have a dimensionless expansion parameter. At high enough order in that expansion parameter, I have amplitudes in which two gravitons come in and n gravitons come out. Okay? And the incoming energy S can be very, very small, much, much less than the Planck mass, much, much less than the string scale. I can take it to 0. Nonetheless, for every value of n, these amplitudes exist, and they're finite. Okay? Now, as a consequence of that, well, furthermore, let me make one more point about these. Because of our belief in effective field theory as a description of gravitational scattering at low enough energies, if I take S small enough, all of the kinematic invariants in this process are arbitrarily small, and I should be able to calculate a leading contribution to it just by using Einstein's Lagrangian. So there are a whole bunch of Feynman graphs, and they contribute, that's what this black box is. It's the contribution of all Feynman graphs that have in graviton external legs in the tree approximation. Okay? That'll be the leading result at low energy, and it's also the leading result at small coupling for a theory that does have a small dimensionless coupling. So now let's compute, using this, the imaginary part of the 2 to 2 amplitude at very low energies, which by the unitarity equation, imaginary part of the T matrix is I times T minus T dagger. This equation tells me that there's a contribution to that, imaginary part of T, which is T minus T dagger, equals I times T dagger, excuse the incorrect first form of the equation. That tells me that there's a contribution to the 2 to 2 amplitude at very low center of mass energy that comes from summing over these diagrams. Furthermore, if I look near the forward direction, then all of these contributions are positive. Exactly in the forward direction, they're positive because they're squares of matrix elements. This is the optical theorem. So I'm not talking here about graphs with supersymmetric partners of the graviton and so on, but those will contribute additional positive contributions to the amplitude that I'm going to calculate. And near the forward direction, there's no possibility of supersymmetric cancellations. So this is a very small amplitude in powers of G or in powers of S over M Planck. But if I count, there is in this amplitude an n factorial. And it comes from permuting these legs relative to these legs. Okay? So these are bows of particles. I have to symmetrize the original state. I fix an order over here, but then there are n factorial permutations of these legs. And so this diagram has two properties. Number one, if I go to high enough order, and higher order, I get a more and more complicated multi-particle cut near the origin of energy. And furthermore, that series of cuts doesn't converge. Okay? This is not a convergent series. And there's a paper that Suvat wrote recently, whose relation to what I'm saying here is not obvious to me, but I think it is somewhat related. So there is a divergence that's coming from the number of soft gravitons.
So there's also an energy factor that comes in the theory of gravity.
Sorry?
There'll also be a factor that comes from the energy in the theory of gravity.
Sure.
And that, if you're not going to scale the center of mass energy, then that factor will be 1 over n, because each is...
That's right.
So there'll be a 1 over n to the n.
Right.
You would actually cancel the n factorial if you don't scale the energy with n at all. See, because there's an s over n Planck, but the s is divided over n particles, so there's an s over n Plancks, that's an n loop diagram. So you get a 1 by n to the n also from just the fact that...
No, I don't think there's a region of phase space where you're correct, but I think that if you integrate over all regions of phase space, there are regions where the energy is carried mostly by one particle.
Well, the question is, I mean, the n factorial of course comes from all diagrams, so what I'm not sure about is whether you can get away by keeping the energy all the way smaller than m Planck and also taking advantage of the n factorial and scaling it. Just because...
I believe the answer is yes.
So how does that... you're just going to look at... You see, if all the energy is carried by one particle, that's... yeah, I'm just confused about how where the perturbation theory breaks down in this limit where you don't scale the energy at all. Now, whenever perturbation theory breaks down, there's usually some way of understanding it through the formation of black holes, which includes also this analysis that we did. But in this situation, there's no black hole formation because the energy is much smaller.
Yeah, I think what this is much more related to, there's a phenomenon we're very, very familiar with in four-dimensional gravity. In four-dimensional gravity, in fact, the conventional S matrix does not exist at all. There are no matrix elements of the T matrix between any pair of Fock space states. infinite numbers of soft gravitons in Fock space language, but they are not normalizable states in Fock space. Okay? So what I'm arguing here is that there is a singularity near the origin which is not explainable by a normalizable state in Fock space. And I think that's true in any number of dimensions. The difference between 4 dimensions and higher dimensions is that in higher dimensions, the S matrix does have finite matrix elements in Fock space, but it also has matrix elements that go out of the set of normalizable states in Fock space. And so the real Hilbert space, Fischler and I have made a suggestion, which I don't have time to go into today, about how to think about the real Hilbert space on which the scattering operator acts, and it's a Hilbert space of currents flowing out at infinity that carry both momentum and other quantum numbers at infinity, where the Fock space states are the very special cases of currents that are infinitely collimated along a particular direction in momentum space. And so the what I believe this is related to is the fact that although in higher dimensions the matrix elements will not have infrared divergences in higher orders, in Fock space, nonetheless there are matrix elements that take you out of Fock space into a space that, in colloquial language, has an infinite number of gravitons in it.
Okay, so if I understand correctly, if you put a finite infrared cutoff, which you can keep as much smaller than S, but you don't scale that with N,
Right.
Then this problem does not occur. Is that correct? If you just put a finite IR cutoff, but you don't.
That's correct.
Then there's no problem.
That's absolutely correct. Yes. This all has to do with extreme infrared physics. In fact, it's clear from that, as goes back to the work of Bloch and Nozick in electrodynamics and Weinberg in gravity, that there's a very easy way to solve this problem in a practical sense. And that is to say, rather than defining S matrix elements, you define inclusive cross-sections, in which I do precisely what you said. I'm going to ignore all gravitons whose total energy is less than some cutoff, which for an experimentalist would be the actual energy resolution of the apparatus. And I'm going to sum over all of the states of those particles, not keeping track of the quantum information in those states, but just assuming they exist in some Hilbert space. So what the description of those states is doesn't matter. I get inclusive cross-sections. If the infrared cutoff is low enough below my detector threshold, that's all I'm going to measure anyway. And those things are perfectly okay, no problem. So it's really the infinitely soft gravitons that are at issue. And the issue with the infinitely soft gravitons is interesting, as far as I know, only for one problem in theoretical physics, namely, is the gravitational S matrix unitary? In order to tell whether the gravitational S matrix is unitary, I have to understand what the Hilbert space is on which it operates, and whether it's a unitary operator in that space. I really have to understand the quantum information that's emitted into the soft graviton sector. That, I think, is the essence of the problem. Okay.
So is this qualitatively similar to QED or only quantitatively? I mean, in the sense that
it's a lot worse than QED. So the arguments I've given you so far work also in QED, right, and they also work in theories of Goldstone bosons. Right. Okay, but in those theories, there are local Green's functions that you can compute, which are totally infrared finite, and you can study limits of those where points go off to the boundary and so on and so forth, and you're getting something no one has ever. There's in QED in 4 dimensions where there is an IR divergence problem. There's a prescription due to Fadeev and Kulish which works in a resummed perturbation theory, It's not proven to work non-perturbatively. Similarly, in theories of Goldstone bosons, people have talked about the S matrix for pions, but there it's really easy because what I can do is break the symmetry a little bit, define a perfectly well-defined S matrix with finite pion mass, and then try to take a limit as the mass goes to 0. So in the non-gravitational theories, problems like this sort of exist in the S matrix, but you can get around them by using the technology of local quantum field theory. In the gravitational case, we can't do that. The only observables are the boundary observables, and we have to understand what those are doing and what the correct Hilbert space is. As I've said, Coolidge and a number of other people have tried to work on the gravitational analog of the Faddeev-Coolidge approach, and there is some sort of semi-perturbative way of dealing with the infrared divergences in 4 dimensions, but that does not at all deal with this extra infrared divergence that comes from the divergence of perturbation theory itself. Okay? Those are all procedures that are meant to give you results order by order in some sub-perturbation theory. The claim here is that non-perturbatively, there's still an issue, which for gravity, we have to resolve by finding out what the real Hilbert space is. Okay. So now, let me assume that I've convinced you, even Subrat, that this is correct. And let's think about this derivation over here. And you immediately see that there's a problem. And the problem comes from the most primitive facts about the AdS-CFT correspondence, namely that the spectrum is gapped. The lowest lying graviton state has a mass or an energy which is related to the dimension of an operator. The spectrum of operator dimensions is discrete. There's a gapped spectrum with a gap that goes like 1 over r. So if I start trying to compute these diagrams, the constituents of this unitarity cut, using these techniques, I fail when n is of order r times m Planck. I simply cannot compute those diagrams and get a result that's anything like the Minkowski result once n is large enough. What happens then is precisely what Suvrat was talking about a moment ago, that if I start trying to see, the big trick in this whole derivation was this little causal diamond in AdS space is one of many, most of which are way out at the boundary. And getting a lot of energy to go into that causal diamond is something you have to work to do. It's a non-trivial thing to construct initial states that will send all of the energy in here into a way which will scatter. But here, this causal diamond has a finite size. The energies have a gap. And so at a certain point, you're putting so much energy into that causal diamond that you start to form black holes. So first you start to form little black holes. That's already a disaster, because those don't occur in these diagrams. So you're not getting the right answer. But it gets worse and worse as I increase n past this threshold, because eventually I form a stable AdS black hole that engulfs the entire arena in which the scattering amplitude was supposed to occur, and I'm obviously not getting the scattering. So I don't have an argument that says, well, okay, let's be very careful, take Rn Planck to infinity, calculate, a finite number of diagrams, try to extrapolate. But it's clear when you're doing that, you're just going to be getting terms in the perturbation series, which diverges. So there's absolutely no prescription that we know of that will really get the non-perturbative S matrix, including all of the infrared gravitons, out of AdS-CFT calculations. calculations.
Okay. You say that to the extent that it mimics flat space physics, it will have the problems of flat space physics.
That's right. That's right. So you can try to take a very careful limit, r goes to infinity, n goes to infinity, such a way that everything looks like flat space physics, but then you'll be calculating actually the perturbative terms in this series which doesn't converge. Okay. So that's the essence of our first argument, that there's a problem. And it, as I said, I believe it depends on very, very little besides kinematics and unitarity, and the fact that near the forward direction you can't get cancellation, so there can't be some magic happening in supersymmetric theories that will avoid this problem. Okay. So now I'd like to turn. Yes.
One more way. I mean, this is a statement that these are capital N point correlators.
Sorry?
This n small n here now is scaling with capital N of the AdS CFT, because this is.
That's right. That's right.
And all of these derivations of flat space are all done perturbatively in 1 over n expansion.
Absolutely.
So clearly, if you start looking at large capital N point correlators, then we don't have a derivation.
Right. Right. So that's exactly. I mean, it's quite clear from every standard approach to AdS CFT that you're not dealing with this problem. And really, the point that we're making is that this is a problem which, if I didn't care about exact unitarity, we could just say, okay, let's calculate inclusive cross-sections. It's not going to change anything. So I could certainly imagine that I can get those inclusive cross-sections correctly out of some limiting AdS CFT calculation. But if I want to know where the quantum information goes in a Minkowski process where I form and evaporate a black hole, that's not adequate.
But just to say about that, I mean, Tom's saying also there's a problem with 4-point correlators, but these n are just the intermediate states.
That's absolutely right.
Also, 4-point correlators is not a perturbative problem. You can compute perturbatively all of these things. There's some problem in checking the non-perturbative unitarity when you start considering intermediate processes which have capital N.
Correct.
Capital N.
But if you just don't think about it, you compute the 4-point function, you compute it however you want, and you still will not get it out.
That's right. You will
You
not.
don't have to look at external observables that happen.
Suppose you've got the exact 4-point function of n equals 48 mils for the graviton operator. I believe this argument is telling you that will not converge to the exact 2-to-2 scattering amplitude.
The exact 2-to-2 scattering amplitude, but the exact non-perturbative 2-to-2 scattering. Certainly, you can extract perturbatively.
Perturbatively, I have no problems with anything. Okay, there is one issue in perturbation theory that nobody's ever dealt with, which, if I have time, I'll tell you about. But certainly.
Yeah, but we don't even have a proposal to check this. If someone gave you the exact 4-point function, we don't even have a proposal to what should one do with it to get the S matrix. So.
Okay. So now I want to redraw this picture, but I want to put some more structure into it. And I want to turn to the second of these papers, which is the first historically. And this was a paper in which Fischler and I were trying to finally address the question of what's the relationship between our holographic space-time formalism and AdS CFT. Now, let me...
Sorry, just to go back to the formula, small n is of the order of r times mp. So isn't that n to the power 1/4? I mean, the capital N to the power 1/4?
This, I'm not talking about... Yeah, I mean, in n equals 48 mils, yes.
So I mean, it's probably that when small n is something, some power of capital N, but not necessarily capital N itself.
Absolutely. I'm sorry if I get the impression that I was saying that it's an n. It's the correct formula is the one written in terms of R in the plane mass. And that's valid for any AdS CFT, not necessarily n equals 4 yang mills. AdS 4 equals S7, AdS 7 equals S4, and so on. So how that scales in terms of the n of the boundary field theory, that depends on the law. Okay. So let me tell you briefly about the holographic.
Is the consequence of what they said that the R goes to infinity limit of this 4-point function is not? Suppose we had n equals.
Yeah, it's not. I'm not sure what it gives.
But it's not some nice smooth effect.
I don't believe that it is the S vector.
But apart from not being the S vector, it's just it will have some singularities. You say because you're saying that there are these singularities from these lower and lower energy particles contributing, and how low they are depends on R. So as you take R to infinity, you get new singularities.
So here's what I really think is correct. Here I have to tell you a little bit about our proposal. We believe that in Minkowski space, actually the thing that's well defined always is the amplitudes for what are called exclusive Sturman-Weinberg jets. That is to say, amplitudes in which operators carrying certain quantum numbers, including momentum, go out in a particular direction to null infinity. Okay? Those operators are measures on the boundary, and a Fock space matrix element corresponds to smearing one of those operators with a delta function. Okay? And so they are things that exist, but they're embedded in a much larger class of amplitudes that have to do with the single particle you're thinking about being emitted, but also emitting lots of soft particles along the collinear direction. Okay. So that's purely hypothetical. That's just our proposal.
Great.
So
sorry, just to re-ask. Suppose I take n equals 4 angles.
Right.
I take 4 stress tensor insertions at fixed points.
Right.
And I take the limit g held fixed n going to infinity.
Right.
Is it a consequence of your statement that that limit will be singular?
I'm not sure of the answer to that. Okay. So what will be true is that there's an amplitude that involves integrals of that over a region in momentum space that will be fine. And you're asking me what happens if I try to shrink that region down to zero size. I don't know the answer to that. It might depend on the dimension. Certainly in 4 dimensions, it won't work at all.
So can I say this limit where you go beyond the closed limit, using lambda to infinity. The AdS 4-point correlation function is something. It's not clear we understand what that thing is in flat space. I mean, it's true that you're taking R to infinity, but we don't have the understanding of, so it's not clear whether it will be well defined or not. I mean, even with the true S matrix observable studies of these jets, we don't know what the AdS correlator is with respect to flat space amplitude at that limit.
But even if I say
It's something. It's some integral of the amplitude.
the top arguments, which are quite general, I mean, if developed, seems to apply to that limit. Whenever you have many very soft particles, this argument will apply. And in this limit, the number of soft particles grows without bound. And so it seems to me that his argument will imply that this is a singular.
There are some objects which are well defined, right, which he's going to argue now. There are some jets if you
But I'm
take
talking about these objects. A stress tensor
But
and x1, x2, x3.
what is this?
Where
one
it's
sensitive?
certainly-
It's one particle. It's an insertion at the boundaries. We don't know what it's.
So Shiraz, what's definitely singular is if I try to take the zero energy limit of these amplitudes, those will be singular for sure. Okay, we see that in perturbation theory, and the singularity will not look like a finite number of particle cut, like it comes from something in Fock space. That's all I'm saying. Away from zero energy, it might define something,
Okay.
but it will not be the entire, what I would consider the proper S operator that involves these jet sort of. Okay, so now I want to turn to holographic space-time. So for a long time, Fischler and I have been thinking about holographic space-time in which one does quantum mechanics along time-like trajectories in space-time. So the quantum theories define time-like trajectory by time-like trajectory. For the purposes of today's talk, you can think of the time-like trajectories as just geodesics in anti-de Sitter space, which are supposed to approach geodesics in Minkowski space, in the limit r goes to infinity.
Sorry, Dr. S. one more. Where in your argument were you using that S was small?
The fact that I know how to calculate those amplitudes.
Okay, so small compared to M Planck.
Yes,
Fine.
right. Or M string.
Fine, yes.
If if I'm in weakly coupled string theory, in order to do the calculation, I have to be small compared to M. So the basic idea is you do quantum mechanics along a time-like trajectory, and for time-like trajectory, if I take any 2 points along it, they define a causal diamond. And the thing that's interesting about anti-de Sitter space is that at a finite proper time, the area of the so-called holographic screen of the causal diamond goes to infinity. In language that you're all more familiar with, in a finite proper time, a photon can reach the boundary. And the boundary has infinite cross-sectional area. So it was the holographic space-time formalism was based on the following idea. We start with some quantum system. It has some Hilbert space. That Hilbert space is defined by what happens to this causal diamond in the limit of infinite proper time along the trajectory. That'll tell you how big the Hilbert space is by measuring the area of the causal diamond. So in Minkowski space, it says, oh, as proper time goes to infinity, the entropy of that Hilbert space, the log of its dimension, goes like time to the d minus 2. And in de Sitter space, the area goes to a constant as t goes to infinity. And in anti-de Sitter space, the area blows up at a finite t of order the AdS radius. Okay. Now, our prescription had always been, we work along time slices that don't interfere with these causal slices. So they're hyperboloids that fit between causal diamonds. And what that means is that at each time, the Hamiltonian has to be time dependent along these time slices. And at each time, h in of t acts only on degrees of freedom or operators that live inside the Hilbert space associated with the small causal diamond between time minus t and time plus t. And then if I go to a slightly larger time, what happens is the degrees of freedom migrate from here to here, and the system h in couples together more and more degrees of freedom. And fewer are in h out. And we always sort of concentrate on h in because that's what observable physics corresponds to for a detector that's traveling along this particular trajectory. H out gets determined by a complicated set of consistency conditions. Namely, you do this for every single time-like trajectory in space-time. And you insist that on overlaps of causal diamonds of the trajectories, there's agreement of what the density matrix is on those overlaps. Now, I don't have time to go into the details of that formalism. Let me just claim that those constraints are very, very powerful. And they actually have physical content and lead to all sorts of nice consequences in the formalism. All I want you to think about now is this split. We're going to ignore what's going on with h out and think about what's happening with h in, because for any given time, h in only doesn't couple in all the rest of the degrees of freedom. So what we're doing is we are taking a system of degrees of freedom, and as time goes on, we're entangling more and more of them together by the action of the Hn, which couples more and more of them together. And then, in AdS space, at some time t of order the AdS radius, the number of degrees of freedom acted on by Hn goes to infinity. Anytime you have a Hamiltonian with a finite number of degrees of freedom and you take a limit, you have to do something special to make that limit converge. And AdS CFT had taught us what you need to do. You have to get a finite system Hn, which, as t approaches this point, will approach a quantum field theory on the boundary. That's what you need to do to make a model of AdS space. We understood that a long time ago, and furthermore, something that was nice, our degrees of freedom were all associated with the holographic screen, SD-2 of these causal diamonds. And the thing that cut off the number of degrees of freedom in our formalism was a cutoff on the SD-2 angular momentum. And so it had precisely the flavor of the UVIR correspondence familiar from AdS CFT. In other words, you have a theory that lives on a sphere. It's got an angular momentum cutoff. As time goes on and you're exploring more and more of anti-de Sitter space, the cutoff goes to infinity. So all of that looked great. And then we started writing the paper that's mentioned over here when I saw a beautiful talk by Jeffrey Vidal on the work by Evansley and Vidal on the tensor network renormalization group. Now, the tensor network renormalization group is something that the basic idea of tensor networks and their connection with AdS CFT is something that was introduced by Brian Swingle, and there's been a lot of work on it. And the basic idea of tensor network renormalization is you think about some lattice system which is sitting at its critical point on a very dense lattice. And you perform a set of transformations on the ground state of this system. The ground state of this system has entanglement between all of the different degrees of freedom. You perform a set of transformations that disentangle the degrees of freedom in a way that gets rid of short-range entanglement, but leaves long-range entanglement. And you get a new coarser lattice which has fewer degrees of freedom entangled, okay? That you haven't, in this way of thinking about things, thrown away the degrees of freedom as you do in conventional renormalization group approaches where you integrate them out. You keep them around, but you make a transformation that disentangles the state so that only a subset of them are entangled together. So if you have been thinking the way I've been thinking for quite a number of years, you say, oh, that's just the reverse of what we've been doing. And so we said, aha, if we could get our system into some kind of lattice form, then we could just get AdS CFT out of holographic space-time by taking the inverse of the Evansley-Vidal tensor network renormalization group as what our Hn of t was. And indeed, if you look at their work, they have a time-dependent, they call it scale-dependent Hamiltonian, which does the decoupling. See, they do this transformation again and again and again, thinning out the degrees of freedom, and they do introduce a scale-dependent Hamiltonian such that at each level of the ring, the state is the ground state of that scale-dependent Hamiltonian. And what they showed quite nicely for very simple models like the Ising model is that once they get it down to a very small number of degrees of freedom, they can diagonalize the scale-dependent Hamiltonian, and its eigenvalues are the low-lying dimensions of the operators in the CFT.
It's what they would be exact or approximate?
Everything they did was numerical, so it was numerically exact.
But the idea was exact.
The idea was absolutely exact. They implemented it by the standard kind of NERA tricks with variational states, and they did that all on a computer. And so all of the calculations are numerical and approximate, but they work. And of course, we don't know how to do this for some serious ADS-CFT, but morally speaking, as Edward Witten has taught us to say, this procedure should work for any conformal field theory.
So where did they put in information about what in the bulk field is?
Sorry?
Where did they put in information in this numerical analysis of what the bulk fields are?
Well,
That
they
goes to that.
start from a fixed lattice theory at a fixed point. Okay? They're never in the limit where the radius is large in Planck scale. They're doing the Ising model. So the number of degrees of freedom is very small. So whether you can say there are bulk fields or not is unclear. You know, if you draw the kind of diagrams that the error-correcting code people make, you could try to associate bulk fields with their transformations as well.
So you maybe understood, but you said the statement about how the lowest lying eigenvalues of the Hamiltonian corresponded to ADS excitation. So maybe I misunderstood you.
Yeah, okay. The point is, as I said, the CFT they're talking about is a soluble one. It's the Ising model on a line, or some simple variance of that. And so they know what all the dimensions are from, 40 years of work on solving for the dimensions, and then their procedure reproduces those known dimensions. Okay. So they're not comparing it to some bulk calculation, and it's unclear whether there's any kind of sensible bulk calculation for something with such a small weight. Okay, so that was our procedure. There's an issue of how you take the momentum space cutoff that we have, the angular momentum cutoff, and turn it into a lattice cutoff. It turns out there's a relatively nice way to do that. I don't think that I want to take the time to go through the details of that. I'd be happy to tell anybody privately. You can go from an angular momentum cutoff to something that defines a non-regular lattice on the sphere. It's not, of course, rotationally symmetric. It's only invariant under certain discrete abelian subgroups. And get a lattice theory that very plausibly will converge to the continuum field theory as you increase the number of angular momentum modes. And so you could follow this path. And so we said, okay, are we done? Is this a proposal? And then we realized there was a very serious problem. Okay? And this is a problem that everybody in the ADS-CFT community who thinks about these things knows about, but I think there's a kind of a bit of denial in the approach to it. So there's a very serious difference between large black holes in anti-de Sitter space and small black holes in Minkowski space. And that difference has to do with the question of the spread of information. So how do we know about the spread of information on black holes? The way we know that is by studying the spectrum and the properties of quasi-normal modes of the black hole. Quasi-normal mode of the black hole is, here's the spherical horizon of the black hole. You poke it someplace locally, and you ask, just in geometry, just by solving the linearized Einstein equations, how long it takes until you can't see that something was localized at some point. How long does it take the information to spread over the whole sphere? And the answer in Minkowski space is there's a natural time scale, which is the Schwarzschild radius, Rs. Everything is going to behave on that time scale because it's the only scale in the problem in classical GR. And then on that time scale, the time that it takes for the information to spread is the logarithm of Rs, if you will, over L Planck. Okay, where that scale doesn't, it's logarithmic in the entropy. This is called, this was first discovered by Hayden and Preskill, and it was analyzed in a beautiful paper by Sekino and Susskind, who gave this behavior the name fast scrambling.
So the time for decay of quasi-normal modes is just Rs, right? Where is that
Sorry?
from? The time for just the classical problem of decay of quasi-normal modes will give you a time scale
Yeah,
Rs.
you ask how long does it take to be unable to tell the local fluctuation from a quantum fluctuation of the field.
So you want the amplitude
That
to
gives
decay
you-
sufficiently.
You want the amplitude to decay, and because it's falling off exponentially, you get a law, but only in Minkowski space. Okay. What happens in anti-de Sitter space? Well, in anti-de Sitter space, there are two ways to do the analysis, which give you the same answer. One of them is to use a very, very general result about anything that looks remotely like a quantum field theory, namely quantum field theory or some kind of lattice quantum field theory with a lattice cutoff, anything that has local interactions on a sphere of radius Rs. There's a bound called the Lieb Robinson bound. Which says that in quantum field theory-like systems, information spreads ballistically at most. Okay? And it's relatively easy to understand how to do this if you think about taking the commutator of two operators, one of which is separated in time, and then calculate this. These things originally commuted with each other, and now, because of the action of the Hamiltonian, they won't commute after some time, and because the Hamiltonian is local, it takes a time that's sort of linear in the distance to get, and the propagation velocity is characteristic of the model, and Lieb and Robinson prove it exists and tell you how one would go about calculating it in a particular model if one had infinite power. There are some things in quantum field theory that spread more slowly than this. Energy, conserved quantum numbers, diffuse. Okay? But the characteristic both of ballistic propagation and of diffusive propagation is that the time in units of the characteristic time scale of the problem is power law in the entropy. Okay? So ballistic propagation is one particular power of the entropy, and diffusive propagation is a different power of the entropy. It's not logarithmic, it's not fast scrambling. Now, in our holographic space-time formalism,
So if I just look at this, say I have a black hole with global ADS.
yes,
I do the quasi-normal mode analysis. Why would I get the same thing here?
you don't do it. It's really, I mean, there's an enormous literature on this. It precisely gives you the ballistic scrambling that you expect from, there are a lot of differences. So for example, for a black hole in AdS space, no matter how large the Schwarzschild radius is, the time scale is not the Schwarzschild radius, it's the AdS radius.
If the black hole is very small, it will behave just like a Minkowski black hole.
If the black hole is very small, it will behave just like a Minkowski black hole in AdS space. The question is, can that behavior be explained by quantum field theory?
Okay.
So my claim is, if I do the analysis for quasi-normal modes for very large black holes, size larger than the AdS radius, then extensive calculation done by many people, much more competent than I, has shown that you do get the ballistic propagation expected from quantum field theory, except for the diffusive modes, which you can also see. And the time scales are just what you expect from quantum field theory, namely it's always the AdS radius, has nothing to do with the temperature, which determines the black hole radius. But the question is, we know from gravity that the small black holes in AdS space will have fast scrambling. How are we going to explain that in terms of quantum field theory?
Sorry, just let me understand the big black holes a little better, please. So, if the black, maybe a little bit the infinite size black hole, is that where the problem is?
No.
Suppose I take
Just
something
take
like
R
10
much
times.
greater than Rs.
Okay, 100 times AdS radius.
Asymptotically large to do the leading large R expansion.
I mean, so maybe that's where. But suppose I take a finite size black hole, 100 or 1,000 times. I've got a discrete quasi-normal mode spectrum.
Right.
It's set, this quasi-normal mode spectrum is set by the size of the black hole. It's set by the size of the black hole probably in an inverse way, because there's an effective length scale, energy scale, which is where you are.
Right.
And the time will be set by the inverse of that. It'll be, this is setting a distance scale that will set an effective energy scale. AdS radius will make up the dimensions. But I would get something like this, I would have thought, at least mode by mode, for any fixed size black hole. Now, when you take the size to infinity, you've got the massless modes of hydrodynamics, and that changes the analysis.
No, that's true, but even without taking the hydrodynamic modes into account, the scrambling of information, not quantum numbers, is ballistic.
Okay, but just
And
one.
it had better be so, because otherwise quantum field theory is wrong, right?
But the quasi-normal modes, except for the hydrodynamic modes, decay fast.
They do decay fast,
And isn't that
much
what you use?
more rapidly, but but they don't decay, they don't spread things over the sphere in a time that's logarithmic.
Okay, so it's what the
Because if
quasi-normal modes are doing. in
If
a
they did, they
positional
would
way.
violate
That's
the Lieb Robinson bound, and the Lieb Robinson bound is a rigorous result in the quantum field.
So there's something I still haven't understood, which is this bound comes from taking the quasi-normal mode and asking when does it decay so that the size of the excitation is as much as the Hawking scale, right? That's where the log comes from. So the
Right.
leading RS cancels the quasi-normal mode, and then you just ask when does it become. If you did the same thing for a big AdS black hole, you would again get log n, where into some number, but you would still get log of capital N, because the typical quantum fluctuations are size 1 by n. The quasi-normal mode frequencies are 1. So you ask how long you have to wait, it's log n, and then you get fluctuations which are suppressed by 1 over n. So whatever fluctuation you start with in log n time, it becomes 1 by n, and that's the
Okay, look, here's I think the point. That calculation is not sufficient to answer the question that I want to ask. So if I ask the question, how long does it take for the information to spread of order 1 AdS radius, then you're right. Okay? But we're asking the question, how long does it take to spread over the whole black hole?
the calculation Subrat's doing is telling you the time that it takes for the quasi-normal mode to decay to almost nothing. Once it's decayed to almost nothing, it has spread over the whole black hole, because you've got the round black hole.
No, I don't think that's correct. It's decayed only out to 1 AdS radius.
On the boundary, it's certainly gone. I mean, the log n is much larger than the time it takes to go down the scale. there's some statement.
Just to say again, because we're probably talking at cross purposes, there's a discrete spectrum of quasi-normal modes at any finite r.
Absolutely.
So just like you had here, we've got the amplitude of that mode is original amplitude times e to the power minus some discrete stuff. Forget about the hydrodynamic modes and it's really discrete. And then if you ask how long does it take for that amplitude to become, let's say, 1 over n prime, you get a formula like this. That I think is you can't avoid. Now you may be saying, now I would have thought that if the amplitude becomes less than 1 over n Planck, we're back to a round black hole because all your perturbations are died away, and then you're left with a round black hole. So I don't see it with a probably big shoot.
No, what I think is happening is that it's not round because the black hole radius is much larger than the AdS radius. So in that time, it's spread out of order the AdS radius.
But like Subrat was asking, are you taking the limit where this r in units of AdS radius has some n in it? If I take the limit to be 1,000 times, then I'm going to much larger times.
Yes, effectively I'm saying yes. I want to take a limit where it's much larger.
In terms of r, which is like n or some n squared.
But r like n is in
No, I
temperature
don't.
with it. You don't want to do that.
I don't want to. I don't want R like.
Poincaré patch type limit.
Yeah.
R goes to infinity is a good limit, right, for these black holes. You just get locally Poincaré patch.
Just get a locally Poincaré patch.
Yeah.
Okay. But
So maybe that's what Thomas. Maybe you got to go to the Poincaré
the
patch.
same property, right? You look at a black brain
Go with the rescale time.
with a rescale.
There's a rescaling in the time. Okay, but I'm also confused.
Okay. Let me say something that I know for sure, which is if I take something that is a quantum field theory or an approximate quantum field theory on a sphere, and I do a small perturbation locally on the sphere, the time that it takes for that perturbation to spread over the sphere is ballistic. It satisfies the Lieb Robinson. That will not behave like this.
So this number will give you something that's much larger. So just to understand that the ballistic bound is telling you the time it takes for something to go around the sphere.
Right.
But this part is much below that, right? Because this will give you a time of order log n. Because Rs by n Planck is, well, I don't know, it's not Rs by n Planck, it's actually Ms by n Planck. So Rs by n Planck also. That's a number of order n. So this is a time which is giving you a time of order log n. That's much slower than ballistically going around the sphere at the boundary. I mean, the time you get from here would be log n. Log of capital N, which is much slower than
Which is much lower than what?
ballistic propagation. On the
Well, it depends on the size of the sphere. The size was 1 then.
Size scale is 1. I mean, I don't know. That's I
So
know
then
ballistic propagation.
slower you mean it takes longer time.
Takes much longer time. I mean,
Yeah, so
there's
I think
some
this is the same question. Is he scaling his size of the sphere?
but there's some natural speed of sound that you would get in the boundary. I mean, there's some you scale the size. This is the conformal theory. So there's some
Right,
natural
but-
speed also.
But if you hold the speed fixed and you take the size scaling within, it takes a long time to be smooth. If you've got a Poincaré patch, you do, let's say, hydrodynamic excitation. You ask how long does it take to reach infinity? It's an infinite amount of time. So, maybe that's
If I could
yeah.
go on, and then we can discuss this later, because I think you guys may understand it better than I do. Let me explain to you something that gives rise to fast scrambling in a very simple way, a very intuitive set of Hamiltonians. So suppose I have a Hamiltonian that's defined in terms of degrees of freedom that I can think of as related to fields on the sphere, perhaps with some angular momentum cutoff. But suppose that that Hamiltonian is invariant under the group of volume-preserving transformations on the sphere. Okay? Or, since I want to talk about a system with an angular momentum cutoff, then there is a finite dimensional group that approximates the group of volume preserving transformations on the sphere. In that case, if I ask the question that I asked about spreading of information, the picture that I drew is very misleading. Because this little spherical cap is equivalent to an amoeba that has the same volume that spreads out and touches whatever you like, just by doing a volume-preserving transformation. And so, in the work of Sekino and Susskind, they made a conjecture that Hamiltonians that had the form of matrix models, traces of products of matrices, would have the fast scrambling behavior. That can be understood in terms of this volume-preserving picture if I think about n by n matrices as an approximation to the set of functions on the two-sphere. Then n by n matrices, traces of products of n by n matrices, are precisely invariant under the fuzzy, the algebra of n by n matrices gives the fuzzy algebra of functions on the two-sphere, and the traces of products, the trace is like an integral, and the traces of products are invariant under a big unitary group, which is the approximation to the area-preserving diffeomorphism. More generally, anything that's invariant under volume-preserving transformations will have this property. The only thing that fixes, once you've insisted on this, the only thing that stops you from propagating information instantaneously is that you've got a Hamiltonian that has a finite number of terms in it. And so in any given term of the Hamiltonian, only some finite number of the variables appear coupled together. And so if I ding one of the variables, act with the Hamiltonian one time, it can only couple to those few variables it's connected to, and then each of those, the next time the Hamiltonian acts, can act on all the ones those are connected to. And that gives me a logarithmic propagation with the number of variables, or logarithmic in the amplitude. And that's essentially the generalization of the Sekino-Susskind work. Now the point is that dynamics invariant under volume-preserving transformations is incompatible with quantum field theory. Quantum field theory, has some rigid geometry, and it has a Hamiltonian that respects that rigid geometry. And that's where the Lieb Robinson down comes from. It comes from saying, I can only propagate, no matter what you do, I can only propagate this much distance in that much time. Volume-preserving invariance, there can't be any meaning to distance. So our conclusion from this was the following. That if I look at this picture over here, the one other thing that I should point out is that we had proposed for a long time a set of Hamiltonians for the Minkowski space version of holographic space-time, which was precisely a generalization of traces of matrices. It's actually a version in 4 dimensions is precisely traces of powers of matrices. In higher dimensions, it's one of these so-called tensor models that Gurau and others invented a long time ago, and which have recently been popularized by Witten and Klebanov. Everybody's working on them now, because they're exactly soluble systems in some sense, but which nonetheless exhibit chaos. So we proposed that in holographic space-time quite some time ago, and argued that they gave rise to this fast scrambling behavior. So our picture of what happens when we're trying to look at this Hamiltonian Hn of t as time gets bigger and bigger in Minkowski space, is that for some times that are smaller than the AdS radius, we just do exactly what we did in Minkowski space. We have a Hamiltonian that does have fast scrambling. It will properly describe the dynamics of perturbed Minkowski black holes. And then, as we approach the AdS radius, where the number of degrees of freedom is starting to become infinite, in order to have a sensible limit, we switch over, we break the volume-preserving mapping invariance, and switch over to a Hamiltonian that just has the symmetries of this lattice that I was talking to you about, and in the continuum limit ends up having full rotational and conformal symmetry of the field theory. And it smoothly goes over from the fast scrambling behavior that you want for small black holes to the correct ballistic scrambling behavior that you get from quantum field theory. Now, the upshot of that, though, for the AdS CFT project is disturbing. Because what it says is, if I take a small black hole, form it, and it's small enough so that its entire evaporation process will happen before times of order the AdS radius, in our formalism, the correct dynamics of that black hole will never be run by the CFT Hamiltonian. It will be run, or even a lattice approximation to the CFT Hamiltonian that might have the low-lying spectrum. It will be run by this Hn of t that has approximate volume-preserving mapping invariance. And so that behavior, according to us, will not be something you could get by taking the final state and running it backwards with the AdS CFT Hamiltonian or any cutoff approximation to it. You have to know explicitly that there's this region that's not described by quantum field theory in order to get the correct behavior of black holes. That's our claim. Okay? And let's see, I've probably overrun my time. Is that correct?
That's right, pretty good. Take the next one.
Well, there's one other little nugget that we pulled out of this story, which was the following. Here I'm going to have to tell you a little bit more about our formalism.
Could I just for this, let me re-ask the question that Subrat asked. Was your problem comparing the timescales this ballistic business with this log? Which one is faster?
The log is faster.
And why is that faster?
Because the ballistic scrambling is power law in the entropy. So the entropy goes like, some power of the size. And the ballistic scrambling goes like the first power of the size. And so it's power law in the entropy rather than power.
Right.
It's power law in the entropy, so it actually scales to the positive part of the entropy.
Yeah, fraction.
Oh, this I didn't understand. I see. So maybe I can understand the bound there. Your statement is that the time it takes for information to propagate around the system it scales with
T goes like R, the size of the system. Okay? And the entropy goes like R, if the system is capital D dimensional, the entropy goes like R to the D.
right. But that's just the extensivity. There's also a right. But there are other factors that go in there. I mean, in particular, I'm just worried about the capital N scaling. So the ballistic propagation surely shouldn't introduce, if you kept the system to be a unit size sphere, shouldn't introduce a capital N in. There's also how many copies.
There is definitely a capital N scaling, but this is not telling you. I'm asking how it scales with the size of the black hole.
Right.
We should sit down and work this out when I'm not standing up here in front of a blackboard. But I think that I'm right about what you're saying. So let me mention one other thing, which is there was actually another old problem with the old idea of getting flat space from AdS, which was that for reasons that heretofore were not understood, in every example we know of, where we can take the large radius limit of AdS, there's also a compact space of dimension 2 or greater, whose radius scales like the AdS radius. And so the Minkowski space you actually get is not the same dimension as the AdS, but it's the AdS dimension plus 2 or plus 3, depending on which version of AdS CFT you're talking about. Now, in the Polchinski, Susskind, et al. Derivation, no one ever touched localized states on the compact dimensions. Okay. They were always talking about states of relatively low angular momentum on the compact dimensions. Okay. To make localized states on the compact dimensions, you have to go outside the approximations that they're talking about. And so it's an interesting question now that we have a different holographic space-time point of view on this whole transition between flat space and AdS space, to understand where those compact extra dimensions come from and whether there will be fast scrambling or not. So now I have to tell you a little bit more about the holographic space-time formula. So if I have a space-time of the form Minkowski space across K, where K is a compact manifold of fixed size in Planck units. Our formalism says that the variables, and let's call it, the variables of this problem should be thought of geometrically as sections of the spinor bundle over the sphere at infinity in Minkowski space and the compact space. Okay. Now, because if I'm thinking about what's going on in a finite causal diamond, which I need to do in order to study this Minkowski to AdS transition, then both the angular momentum here and some set of functions on the compact space have to be cut off in some way. And I proposed a long time ago with my student John Kepes that the way to do the cutoff was to look at the spectrum of the internal Dirac operator and make a cutoff of the internal Dirac operator in a way that told you things about the shape of the manifold. So for example, if you're on a torus, you cut off more momenta on a short direction of the torus and fewer momenta in the big direction of the torus if there's a discrepancy between the two sizes and so on. Some way of making a cutoff. So the variables are labeled by psi omega sub A, where A is an index that labels some cutoff version of the spectrum of the Dirac operator on the internal manifold. Okay. Omega is the angle on a sphere, and that sphere, since we're in Minkowski space, that sphere becomes arbitrarily big as time goes on, and I look at larger and larger causal diamonds. So the cutoff goes to infinity. But for any finite causal diamond, there's a finite angular momentum cutoff as well. Now what happens, suppose this label is not here at all. Okay. I'm trying to describe a theory which has a radius large compared to the AdS radius. Let me suppose this label was not here at all. What would happen as I took the angular momentum cutoff away to infinity? I would get a field theory of essentially one or some small number of spinor fields on the boundary. Well, I can make a conformal field theory out of that, but C, to use a scare quotes, the thing that counts the number of degrees of freedom of that conformal field theory, will not be large. It will not scale in any way with the supposed radius of AdS space, which is supposed to be large. So I've showed you how to make something whose dynamics gives you a large AdS radius out to the AdS radius, but then that I get, if I don't have this extra label A, I get an inconsistency with the AdS CFT measure of when is the radius large. The AdS CFT measure of when the radius large comes from the computation of large black hole entropy. And it says I have to have many, many fields on the sphere. So the only way to do that is by having many, many modes of the internal Dirac operator, and given the relationship between the cutoff and the internal Dirac operator and the size of the internal manifold, that means a large manifold. And so we claim that thinking about putting together what we know about large radius from the AdS CFT point of view with what we've just learned from the holographic space-time point of view, we will only get a consistent large radius model if we also have a large compact dimension. And there's a little further argument that I'm less certain that this is correct, that if you just have one large compact dimension, you won't really have this volume-preserving mapping invariance that allows you to do fast scrambling, because there's a natural ordering around the circle, whatever you do with its geometry. And so, just continuity prevents you from messing up the points. So at the end of the day, we think that there's a quasi, I would not call it a derivation, but an argument from the HST point of view for why we need large compact dimensions every time we have a large AdS. Okay, let me stop there.
Questions? ICTS questions? It just automatically calls.
Hello, can you hear me?
Yes, I can hear you.
Yeah. So I wanted to ask this question about there is this question about long tail in hydrodynamics that people talk about. So what is the relation, if any, between that and the phenomena that we have discussed?
Yeah, I think the hydrodynamics, actually if you read the paper that we wrote, the 1611 paper, we say, oh yes, the scrambling in field theory is diffusive because of hydrodynamics, and that I think is a red herring. Those are particularly slow modes of spreading just of the information about conserved quantum numbers. Most of the information in a quantum field theory spreads much more rapidly than that. It's with a smaller power of the entropy given by this ballistic Lieb Robinson bound. And so the scrambling of information in quantum field theory is, it still bugs me a little bit that you can transport information without transporting energy, but it's true. I mean, if you just think about how long it takes two operators to develop a non-zero commutator, if they're separated by a certain space-like distance, that happens much more rapidly than hydrodynamic flow.
But there are also the sound modes of hydrodynamics that go linear in distance.
Yeah.
So that would match with your legal.
Oh, you say that matches.
Yes.
I think about the phonons rather than the diffusion.
Yeah, there are two kinds of modes of hydrodynamics, right? There are sound modes and shear modes. The shear modes are the diffusive modes.
Yes.
Omega goes like this.
Very good, very good. So you say I can transport energy ballistically
Yes.
through photons. Thank you, that clears up. Okay, so he gave you a better answer than I did.
Yeah. So my question was about, like, so there's some, it is not completely clear what in gravity should match with these long tails. There's a problem there.
What are the long tails you're talking about, Loga? Are you talking about like the one loop renormalization effects in hydrodynamics? Like the hydrodynamic modes running in loops roughly? Are those the kind of things you're talking about?
From that point of view also.
Yeah, okay.
Yeah, so, but how do we think about it from gravity? I mean, how do you think about it from the ADS? I mean, it's also related to the fact that, this kind of statement that you can make that you don't expect the decay to go, infinitely long because of the,
This is
it needs to stop, right?
sorry. This is now there's something I didn't understand. So there's one limit which certainly comes, which is an exponential limit, which is that there's a fat tail. You don't expect the quasi-normal decay to go forever because there's some unitarity power. So that's not what you're talking about. There's something else.
It is related, yes.
It's related. Oh, I thought you were talking like a one loop effect. Your term is something e to the power
E to the minus n.
Yeah.
So, are you talking about the e to the minus n effect or some other effect? There's some
I'm talking about e to the power minus n effect.
Oh,
e to the minus n effect.
The things which are hard to compute from gravity.
Uh-huh.
I think probably what you call one loop effects is you can just get it from
Yeah.
gravity by this.
so the e to the power minus n, but like in Maldaceno's picture, would be the mixing with thermal ADS, right? That kind of stuff?
Right.
Okay, it's
Yeah.
worse than
Okay, yes.
Or whatever. Something they were. Yeah.
mixing with thermal ADS does not account for the actual
The actual
behavior
fluctuations,
of
yes.
fluctuations.
It just averages them out.
So,
So the question I was asking was that is that related to what we are discussing here or is it unrelated?
I don't think that it's related. What I'm talking about is much more coarse-grained than that sort of stuff. You're talking about details of the fluctuations, whereas I think I'm just talking about kind of average behaviors. So the scrambling behavior is it's very universal, and it doesn't depend in detail on the spectrum and so on. I don't think that it is it's related to things that have to do with the fluctuations in correlation functions.
Okay, it turns out this room is needed soon. So urgent follow-up questions from ICTS or urgent questions from PI.